Hello, everybody. Good morning, good afternoon, good evening, wherever you're coming from to us from. Good to see folks here. Feel free to say hello in the chat, especially if you're new. I always like to say if you're new, say hello in the chat. Let us know where you're coming to us from. We are definitely open to all. Today we're going to talk about counting things. So this stream is all about problems on Rosalind that are towards the start of the problem tree, but that are connected to asking the two questions, which is number one, how many of something are there? And number two, if we can figure out how many of these things there are, can we actually create all of them? So that's a question that's called enumeration, which is to actually construct all of the objects that you think that you can count. So we'll see that as we go through it. That subject is very closely connected to the subject of my own PhD. So my PhD comes from math, and a lot of the problems on Rosalind, you may have noticed, are going to be heavily or sometimes quite mathematical, and that's going to be the case for the problems that we look at today. Now, if you're interested in following along, note our pinned comment in the chat, because that's going to have some starter code for you. We also have been building this with some completed code, so I will always put my completed code from what we do. I'll put a little comment there to a different drive folder, and once we're finished here, I'll add all of my completed code over there. So you can always follow along there if you don't quite, whether you're typing along with me or just sort of following along, you can grab that code always and run it yourself. The next thing I would say is you've got that starter code in the pinned message, and the problem IDs that we're going to solve today. So we're going to be solving Fib, PERM, LEXF, Sine, LEXV, and FIBD. They're all related to the problem of counting in some way, and they all have like a biological flavor to them, but they're all mostly around how it is that we count something or how it is that we enumerate something, which is coming up with the list of all constructs, where at the end of this we say how many of these things are there, and that counts what we want. So we have a fair amount to do. I think a lot of these streams, I'm going to try and solve like 5 or 6 problems. What that means is as the problems get more difficult, we are going to need ways of using solutions to problems that we have already seen and building upon them. That's something that we're going to see today. And the other thing that I would point out is I may touch on some subjects that as we get more advanced, I may not do a full treatment of every in-depth, doing a deep dive into every specific computational technique that we get into. That is the purpose of our parallel project, which is programmingforlovers.com. So if you check that out, we have an entire curriculum that we're building out in parallel. So we stream on Monday evenings, and we have a parallel curriculum there that's all about, from the ground up, how is it that we solve problems in Python that are motivated by science, where we take one small step every time that we go. Some of the times with some of these streams, we're going to be taking larger steps, and that's okay. So if you're interested in more of a fundamentals approach, check out our project there. We're making tons of changes like every week and improvements. You can join our mailing list as well. There's a link to that in the description of this video, and as well as you can sign up on our Programming for Lovers website. That's a great way to just stay in touch with us about all the things that we're doing. So I'll send emails a couple times a week around what are our streams this week, what's our pacing, and we're going to be rolling out a lot more educational projects around this. So make sure to join our mailing list. It's the best way to stay in touch with us. If you're interested in a deeper connection to what we're doing, like on the Programming for Lovers side, we have the opportunity to complete a project, and we have a free or an ebook that comes with the project as well that we're constantly adding content to and developing. And you get access to those by becoming a member of our Philomath project. So there's a link to that too, where in our description, where you can check out that link. And if you're interested in sort of, completing our curriculum and then also getting like one-on-one support from a teaching assistant who will guide you through a programming project, you can join us there. In the meantime, I think we're about ready to get started. As always, please like and subscribe here on YouTube. Feel free to say hello in the chat or ask us some questions as we go. Probably what I'll do is I'll have some opportunities to ask you a question, and then in between problems, if you have any questions in particular, please chat those over to us, and we're happy to help. So I think we're about ready to get started. Julia, welcome from Belgium. And otherwise, I think we're good. So let's count some things and let's code. Our first question that we're going to look at is a Fibonacci question. So, and I'll close down some of these other previous files that we had there. But our first question that we're going to look at is this Fibonacci question that has the ID FIBD on Rosalind and presents the problem of counting the number of rabbit pairs under this hypothetical circumstance that you start off with one collection of rabbit pairs, and then after a period of time, once the rabbits have reached reproduction age, which happens in a single month, we have this not tremendously high resolution image, but here are a collection of pairs. We have an initial pair that grows to adulthood, and then they produce their own offspring. And in every generation, everybody that has reached adulthood will produce offspring. So in the next generation, we have the same adults will survive and also produce a pair. Our young here grow to adulthood and then produce a pair in the next generation. These grow to adulthood and then produce an offspring. So you have what appears to be kind of an exponential growing process. And the classic formulation of this in terms of Fibonacci is, well, in every generation, every adult pair is going to produce one pair of children. But how this question works is to give us a little bit of a different angle on it, which is to say, well, what if we also take as input here a parameter k that's an integer? And that parameter k is also going to specify that you don't just have one pair of rabbit babies every generation, but all of your adult rabbits are actually going to produce k pairs of rabbits. And so my question is, we're given the sample data set, and we have n is equal to 5 and n is equal to 5 and k is equal to 3 here. And our sample output here says 19 is going to be the correct result. So my question to you, here's a good warm-up question, which is, when we're presented with a problem like this, what's the first thing that we should do? I know that I kind of understand how this is going to work. I know that I'm presented with a number of generations, which is n, and the number of rabbit pairs that each adult rabbit pair produces each generation, which in this case is 3. And the answer here in the sample output is 19. What is it, though, that we should do first if we're presented with a problem like this around counting something? What ideas do you have? Again, I think I've got a clear specification of the question, right? But I want to know, how is it that I count for a general N and a general K? How is it that I would be able to produce this output? Now, I want to be able to write code for this, right? And actually solve this problem computationally. But the question is, where would I start? What's the first thing you would do? Is there an equation? Well, we just trust the math people. That's not tremendously empowering. We want to try and come up with an equation ourselves, right? We could surrender. That might be the general consensus here. All right. Well, this is indicative. It's a good sign for why we're doing this, which is no one has any real answer for how I would start to solve this question. Fair enough, right? And if that's the case, then here's an opportunity for me to show you how I would go about solving a question like this, which is not to look up something advanced, not to try and just search for a math answer here that I may or probably actually will not understand. What I would do is I would try to count by hand for this particular inputs. I try to figure out how is that going to actually give me the thing that I want to count. So if I have 5 generations and I have 3 rabbit pair babies being produced by all the adults every generation, I'd say, how does that produce the number 19? If I don't understand that, I shouldn't be trying to solve a problem. And I think even someone who, is relatively advanced as a problem solver probably would just take a moment and try to make sure, do they understand the question? Because I know, for example, the internet understands the question. I know AI knows how to solve the question, but that doesn't help me become smarter. And so for me to become smarter, what I need to do is I will just come into my VS Code folder, and I'm just going to start creating a table that says, well, why don't we say, I'm going to keep track of the month and the pairs. And I will say, let's say at month 0, we're going to have 0 pairs. That's fair to say. And at month 1, I'm also going to have 1 pair. So this is the birth of our initial collection of rabbits. And then from this point forward, and I'll specify this in a comment. So let's assume that K is equal to 3. And this is the number of pairs each adult pair produces. Okay. So this will allow me to continue counting these things to say, if I can't get that when the month is 5, the number of pairs is equal to 19, then I need to start over. I can't proceed until I'm able to do that. And so I can do this by saying, well, when the month is equal to 2, how many pairs are there? And in this particular case, well, these babies have just reached adulthood, so the number of pairs is still going to be equal to 1. And then when the month becomes equal to 3, now I'm going to say I have the currently alive collection of rabbits, but then the rabbits that I had that were born here have now reached adulthood. So as a result, I'm going to know that everybody that was alive in this generation is still going to be alive and definitely will be adults. So I'll know that this is equal to 1 plus 1 equal to 2. We get everything that was alive in the previous generation is going to survive, and everything that was alive in 2 generations previous is going to produce kids. So this is the classic Fibonacci way that we're representing it, except we're changing it here to say, well, actually, everything that was alive here is definitely an adult, and they're going to produce 3 pairs. So in this particular case, I'm going to change that to say it's 1 plus 3 times 1, and in this case, it's going to be equal to 4. Then when I go to month equal to 4, I'll say how many pairs are there. Well, I'm going to use the same sort of logic. I'm going to say there are all of the rabbit pairs that survived from the previous generation, so 4. And then I'm going to have all of the pairs that were alive 2 generations ago, because those are going to be the things that are adults now. And I'm going to say 4 plus 3 times that number, which is equal to 7. And then when I get down to month equal to 5, I'm going to apply this same sort of idea again. So everybody that was alive in the previous generation, which is 7. And then I'm going to say who was alive 2 generations ago. That's going to be the adult rabbits in the current generation. And each one of them produces M, or I should say K, copies of themselves. So K pairs of rabbits. So I'll say 3 or K times this. And so that's 7 plus 3 times 4, which is equal to 19. And the good news is that now that matches what I saw in terms of the sample that I was given. I was at least given a little bit of information here, which is that for n generations equal to 5, and 3 rabbit pairs being produced by every collection of adult rabbits, at this point in time, I know that the answer should be 19. So I should feel like I'm at least on the right track. And then the question becomes, well, what is it that I'm actually doing at every stage of computing these values that I'm doing? Notice that we saw that there was a pattern in what we're doing. So in other words, if I were to continue this process and say in general, is there a pattern that at month n, we're going to have something that we can represent this in terms of what it was that we were doing. And remember at, say, month 5, we said, well, you have the number of adults from the previous generation. They're all just going to carry over. And then you have everything that was alive 2 generations ago, because that corresponds to all the things that are adults now. Each of them are going to have 3 pairs of babies. And so in this particular case, we know that we could say, well, it's whatever the population was in the previous generation. That's going to be the collection of things that have survived. And then we also want to look at the generation 2 generations ago, look at the population then. And we want to multiply it, in this case, by 3, but it's not hard to see that in the general case, we're just going to generalize this into the parameter k. So we're going to say in month n, we'll get whatever the previous population was, and then whatever is adults, so whatever the population was 2 generations ago, times the parameter k. So in general, what we're getting here is a special type of formula called a recurrence relation. And the recurrence relation here is a formula where expressed, I should say, in terms of smaller inputs to the same function. Okay, so, and smaller is sort of up for interpretation, but in this particular case, I could define population of n is equal to the number of pairs alive in generation n. And in this case, what I found is that pop of n is equal to pop of n minus 1 plus k times pop of n minus 2. And that's going to be really useful for when I compute my rabbit pairs collection. The reason why is that, well, there's actually a greater lesson in this particular problem, which is when you look at our starter code here, what you'll see is we have a function that's going to take n and k as inputs, but I'm not necessarily just going to produce, like if you look at the problem is looking for a single value of 19. I'm not just going to produce that one value. What I'm going to do is I am going to produce everybody in this table. And then I'm just going to take the final value. That's going to be very useful because it means if I make a mistake, it'll make this much easier to test. Because, for example, I could just look at the first place where I disagree with a small test that I write by hand. And then the question becomes, how is it that I find what my issue is in that particular case? But in the general case of solving this problem, I'm just going to take the last value in this big list of integers that I'm going to produce, corresponding to the population at every point in time. So to write this function, the first thing I'm going to do is to say, let's call our list, I could call it population. I'm just going to call it Fib, since this is a modified version of Fibonacci. And so I'm going to declare a collection of zeros having length n plus 1. You'll notice in this particular case, I'm going to have this extra month equal to 0. And so when I was looking for month equal to 5, we're going to have 6 total values. So I'm going to have one additional value. And I'm always going to set fib of 1 equal to 1. So this is our initial pair of rabbits. And we start with no rabbits. So fib of 0 is going to be fine to be equal to 0. And then we just have the process of going through the remaining values of the list. And what I will do is I will use the recurrence relation to set the values. So in this case, I'm going to say for, I can use a value of I in the range starting at 2, going up to and including n. So I'll have n plus 1 as the highest index here. And here's where I'll just say set fib of I equal to fib of I minus 1 plus k times fib of I minus 2. We're able to apply the recurrence relation that I established here. And at the end of that process, I'm going to be setting successive values in my list. At the end of that process, I'll just return the entire list. Okay. And if you look in main, we're not interested in returning the entire list, but I'm going to go through the process of establishing this list of integers by calling rabbit pairs and then printing the whole thing. And then I'm also just going to print the final value, because then I'll make sure that for these individual values that it's equal to 19. So I can save this, and you'll note I've also got a little bit of extra code here that's commented out, but I'm going to come into my terminal, and in this case I'm going to Python 3 fib.py, and you'll see that here are the values 0, 1, 1, 4, 7, 19. That's because I printed this list, and that matches the collection of values that we see here, 0, 1, 1, 4, 7, 19. And the final value in particular is 19. So I should feel good about what we're doing. And if we're in good shape, then I'm going to come back to Rosalind and download a data set. So while I download this data set, I will point out that I actually have a little extra code at this point in the project. And one of the things that I have in the starter code is something called custom IO, which is going to handle a lot of the input and output for us. So up till this point, I've had to manually copy over a lot of data. And as these data sets, input data sets and output data sets are going to get bigger, it's going to become a whole lot easier to just download the file. And I'll take that file that I just downloaded, and I'm going to place it into my code folder, and then I'm going to rename it. I think I always want to rename it something like dataset.txt. So the starter code is going to look for a file called dataset.txt. And you'll see here is our input data set. And I won't talk so much about how this parsing works. You're more than welcome to consult it. What we're going to do is we're going to add to this over time, but we're also going to reuse functions that we see in different contexts. So for example, in this case, if you look at our data set, we have 2 integers. Well, presumably we might see other cases where the data set just has 2 integers in it. So we'll have a function that parses a file that has 2 integers in it, and that's included in custom IO. And notice we'll have, for example, one that parses an individual integer, something that parses both an alphabet and an integer. These are the sorts of things we're going to see throughout. We're not going to focus on this code because it's extremely boring, and we just want to look at solving the problems. So meanwhile, I do have a 5-minute timer that I probably should pay attention to, and that means that in Fib, I have, at this point now, a little bit of extra code at the end that is contained in a doc string, which just means that it will be commented out. That's going to handle this. So when I uncomment that out, I have a little bit of imports where I'm importing both this parse2ints function to read from the file, as well as something to write a result to file. And this is going to write it to a file in the same directory as a result. So we both call the function and then print the desired result, so you'll be able to see it in the console, but it's also going to get printed to a file. So when I run this code now, and I probably should save it, but when I run my code, I'll see that this hopefully correct answer gets printed to the console, but I will also see it printed to an output file. So if this becomes, lengthy output, I could, for one, I could upload my file. For now, I'm just probably going to select what we have, go back to the platform, and I still have 2 minutes here, copy my answer in, submit, and see that I solved the problem and got the amoeba achievement. Hooray for that. All right, so we're growing as an organism. We're up to an amoeba. If you have any questions on this in the chat, let me know. We move generally a little quickly. I'm also going to show you a different way of solving this question before we proceed, because it's going to be really useful, both in terms of learning and in terms of some of the other problems that we're going to solve. Now, this is not the only way of solving this question. So I want to show you a different way, which is that whenever you see a formula like this, where you're expressing something that you want in terms of other things that are maybe smaller values. So whenever you have a recurrence relation like this, there is a natural additional way of solving the question, which is to use something called recursion. So I could also write, and I'm going to borrow all of my doc string and so forth, but I'm going to say, let's call this function recursive rabbit pairs. I'm going to say that this recursively computes the number of rabbit pairs. Everything else is the same, and the input and output is going to be the same, and the problem is still going to follow this Fibonacci recurrence. But instead, I'm going to write a recursive function. And what this recursive function needs to do is, in this particular case, I guess I am changing this to be just a single integer. So I'm not going to compute the entire array. And I guess this is at month n. And in this particular case, we know that there are two things that every recursive algorithm needs to have. It needs to have a base case. And the base case is going to be, well, if n equals 0 or n is equal to 1. And so if n is equal to 0, then I just want to return 0. If n is equal to 1, then I want to return 1. And now the meat of the algorithm is the inductive step. Okay. And the inductive step takes this same recurrence relation that we have. And remember that recurrence relation says that the ith Fibonacci number is equal to the previous two, okay? Except we don't have access to the full array now. What we can do is we can call the function. So I could say what I want to do is return recursive rabbit pairs of n minus 1 plus k times recursive rabbit pairs of n minus 2. And you might worry about, making sure that these values actually exist. But note, at this point in time, if we're here, we can assume that n is greater than or equal to 2, which means that this is definitely defined and this is definitely defined. So if n is equal to 2, we'll just hit base cases in either case and we'll return 1. If n is equal to 100, then we're just going to call the functions on recursive rabbit pairs of 99 and recursive rabbit pairs of 98 and multiply that one by k and then add the two things together. So we have an even shorter function, which is nice. And we can even run this. So I could maybe uncomment or comment out my code that I had here. And I could also print recursive rabbit pairs of n and k. And I want these two values to match. So if I save that and I run it, I'm missing a required positional argument. That's not good. I thought I had one. K. Where's this line? Line 72. Need to specify k here. Okay. So that k is not going to change. Now when we run it, we see that we get 19. And it matches. So all seems to be well. There's just one problem. Just one little problem. Tiny little problem. Anybody know what it is? No thoughts? All right. And there we go. Recursive algorithm doesn't scale well. Now that's not necessarily always true, but it's sometimes true. And so let's see what happens. So for example, if I plug in n is equal to 10 and k is equal to 3 and I run this again, everything's fine. We get that the values match. And if I go to 30, then they match. I go to 50. Then at this point in time, you'll see what has happened here, which is that the first print statement has happened, but the second one has not. I'll Control C and show you exactly what I mean. So I've run the first algorithm, now running recursively. And you'll see that print statement happens, but you do not see that the number of rabbit pairs gets printed. So we can compute this practically instantaneously with our first function, and yet the second function we're having to wait. And the question is why? And I've asked this question to students over the years because this is a perfect example of an instance where recursion is not an approach that we want to apply, at least not in the classic sense. And the best answer that I've ever had was actually just a 3-word answer. And the 3-word answer was big tree bad. And so here's a figure that shows what's going on behind the scenes and why this is so slow. Because when you have this sort of structure where you have a function that's calling itself with an input of n-1 and with an input of n-2, so the Fibonacci of 7 is calling Fibonacci of 6 and Fibonacci of 5. Fibonacci of 6 then calls Fibonacci of 5 and Fibonacci of 4. Fibonacci of 5 calls Fibonacci of 4 and Fibonacci of 3. None of these function calls know about the other's existence. And that's not good because you have repeated calls. Look at how many times, for example, Fibonacci of 3 winds up getting called as part of this tree of function calls. So the issue becomes, well, you only have 5 calls to Fibonacci of 3 in this particular case. But it's because the input here is only equal to 7. As the input here grows, then the number of elements in this tree is going to grow almost like 2 to the n, which is really bad. And you're going to have, when you get to Fibonacci of 50, you're going to have like millions upon millions of calls that are all repeated to some of these functions that are going on under, behind the scenes. So even though the program is fast when we write it in the way that we started with, when we switch it to a recursive approach, it's not going to work. A lot of times students come, see that and they take away from it that recursion is a bad approach. That's not true. In fact, what we're going to see is, for a few of our next problems that we consider, recursion is a great approach when it's applied correctly, but we always want to make sure that we're wary of the big tree bad. So anytime you have repeated function calls in a structure where your function calls start growing like this tree, then you should be very wary that you're going to have an exponential growth process in terms of the number of calls that you have. And in this particular case, even though we were just calling this for n equal to 50, I'm going to have to stop the algorithm and show you again that if I comment it out, and run it again, we get an immediate answer with this other approach. So recurrence relations are a good idea. And if we have the issue of big tree bad, then the way to solve this problem is instead to come at it from the perspective of producing this entire array or list where I'm computing values bottom up, applying the recurrence relation. So that's what we did here, where we made the entire list of values. And instead of starting at the top, instead of starting at Fibonacci of n, I started at Fibonacci of 0 and 1, and then I went to 2, 3, 4, 5, 6, 7, 8, 9. So at every point in time, I've already set the 2 values before me. There's no repeated calls, and I create a list. This is called dynamic programming, and it's one of the things that throughout the platform we have applications of, in particular because algorithms like the ones that are used to compare genes, as well as a host of other biological applications, relies on this paradigm. So this is our first foray into seeing dynamic programming, but what we want you to remember is dynamic programming means takes a recurrence relation and applies it to compute values in an array bottom up. There are more precise definitions of what it is, but for now, I think that that's a very workable definition of what dynamic programming is. And it doesn't mean that recursion is bad. It doesn't mean that recurrence relations are bad. But in this particular case, when we see that we have a big growing tree with repeated recurring recursive calls, then we're going to want to use dynamic programming instead. All right, we're going to move to our next question. Any questions on anything so far? How are we feeling? All right. So let's look at another question then. The next question we're going to look at is going to be the PERM question on Rosalind. And what it asks us to do is for an ordering or the collection of the first n integers to tell us not just how many permutations there are. What is a permutation? It's an ordering of this collection of positive integers. So for example, 5, 3, 2, 1, 4 is one of length 5. But the problem goes beyond that and says, can you produce a list of all of the permutations of length n for our input integer n? So the sample data set shows us that there are 6 permutations, and in fact here they are. This is motivated by genome rearrangement studies, which was actually the subject of my own PhD thesis, where you have different possible orderings of a collection of genes or a collection of synteny blocks on, say, a chromosome. And what this is getting at is to show that the number of these orderings is actually going to grow very quickly as the number of genes or the number of blocks grows. The first thing we probably should understand is why, if the input integer n is 3, why is it that we see that the number of permutations is 6? That would be my question 1. And there's a general formula here, which is that we have n choices for the first element. So if you think about I'm picking my permutation, I have n choices for the first element. Then I have 4 elements remaining. And from those 4 elements, I'm going to be able to say I pick one of them. So I have 4 choices for the next element. Then there are 3 remaining. So I pick one of the 3. Then there are 2 remaining. So I pick one of the 2. And then there's 1 remaining. And then we apply something that's called the product rule in counting that says that as those choices, since those choices are essentially independent of each other, then the number of choices that you have is equal to the product of all those numbers. So as a result, for this number of permutations of length 5, we have that the number is equal to 5 times 4 times 3 times 2 times 1. So we're sort of whittling down the number of options at each point in time. And in general, for an arbitrary n, we're going to have that the number of permutations is equal to n factorial. Why? Because we have n choices for the first thing, then n minus 1, then n minus 2, and so on, all the way down to 2 and 1. And the problem here, though, is not just counting. So this would be an easy question if we asked how many permutations are there. But instead what we're going to ask is how many permutations are there, which is n factorial, but how many permutations do you find? And what we're trying to encourage you to do is to solve this question, which is called enumeration, listing out all of the different constructs that you care about. And then if you count these up and you get n factorial, you know that you have a good chance that you've solved the question as long as you haven't duplicated something or something. So you have a quick check to make sure that you have the correct number of permutations down here. But this is a more general version of counting called enumeration, where you list out all of the things that you care about. So we can take this and then try to solve a problem involving producing all of these things. And the question is, how do we get at this? So our idea is going to be to notice that there is some, in the same way that there was substructure when we looked at the Fibonacci numbers, there's a little bit of substructure here. So I could take each of the integers 1, 2, and 3, and we can return these permutations in any order, but I could look at 1, 2, and 3, and then I could take all of the permutations of each of the remaining 2 elements. So I could then just stick 1 at the front of all of these. So what I could do is I could take each of the integers from 1 to n, pick 1 away, and then take all of the permutations of what is remaining. So that's going to be our approach. And in the same way that we wrote a recurrence relation for Fibonacci, we're also going to have a recursive type approach for this problem too, except that, especially because the input size is small, this is certainly going to grow very quickly. But here's where recursion is going to offer us a better solution. In fact, if you try to solve this problem without recursion, it winds up becoming extremely complex. So I would not suggest to do that. But what you're going to see is, actually with recursion, by thinking of this as taking each symbol, pulling it away, and then adding it to the collection of permutations of the remaining integers, it's going to be a much shorter function than you might ever imagine. And this is contained in perm.py. So this function is going to take a collection of things that we want to find all the arrangements of, all the permutations of. And then it's going to produce a list of things. And what the list of things are is permutations. So it's a list of lists of integers. And we can ensure that, of course, at the end of this, we should have however many things are in my collection of elements, which are my integers that I'm going to be rearranging. And we should know that it's the length of that thing factorial. And now to write that function, I'm going to think about this recursively. So I'm still going to have a base case. And that's probably the easiest part of the function to write, which is the base case says, what if the list has only one element? So in that particular case, I'm finding all permutations of just one thing. And so if there's only one element in my list, I want to return a list of things that just consists of elements. Now, elements only has one object in it. So in this particular case, this is a list that only has one thing in it. And at the end, I'm going to return a collection of lists. So it's just the elements list that I already have. The trickier case is the inductive step. So the inductive step here says pull away one symbol at a time. And then we're going to find all permutations of what is remaining and then add it back to all of them. So I'm going to have a function here, or a loop, that's going to say for I in range over however long the collection of elements is that I want to permute. And I will start with defining a result list that I care about. And I can even be more precise and specify, I know what its type is going to be. Its type needs to be whatever it is that I'm returning, which is a list of lists of integers. And then at the end, I'm going to return result. And then as I range over the collection of integers in my input list, this is me pulling away one symbol, I'll say, let's pull away one symbol. And what is that symbol? Well, it's just elements of I. And then I need to specify what is remaining. Okay, so what is remaining is a list formed by everything that goes up to but not including I. And in Python, we know that the upper index, as in most modern languages, does not include the current element. And we're going to go to I plus 1, and then everything past that. So we're going to look at the prefix up to but not including I, and then the suffix of this collection of integers starting after the first symbol that I care about. So this is like the n-1 symbols remaining. And then what I want to do is find all permutations of these integers. So to do that, I'll say subperms is equal to, if only I had a function that would do that. But the function now is where I can rely upon my recursive call to the function that I'm in, which is permutations. So I will trust that it will give me that collection of permutations. So I'll say permutations of whatever is remaining. And I'm going to call that subperms. And now I want to range over all these permutations and stick the first symbol back at the front. So I will, and you could put it at the back too, because we're not specifying that this has to be in any particular order. So there's nothing there is nothing special about the front, but I'm going to say for everything that is in the subperms, well, I'm going to result.append, taking that first symbol and it needs to be as a list. So it's a list first, and then plus whatever the rest is. So remember, the subperms is going to give you a list of lists of integers. And so rest, just say rest is a list of integers. Okay. And this first, I think I called it first symbol. So Python allows us to combine two lists in this way by just concatenating them together. And so this corresponds to just plugging that first symbol on at the start. But I have a list here with rest, and so I should have a list here as well. Now we can save that. And I can Python 3 perm.py and run it on a sample data set. And what main is going to do is it will print the length of the permutations first. So this should be n factorial. And we can see that that indeed is getting printed here as n factorial. And then we're also going to just range over all the permutations and print each one. So what's nice about this is that also matches the format that we have. So this output appears to be the same as the sample, and we should be feeling good about our code. So I'm going to download a data set. And I'm going to come back into VS Code and copy that data set over. So you get the File Explorer up. And I'm going to bring it into our File Explorer. I'm going to delete my previous data set. I no longer need it. And I'm going to rename this dataset.txt. Now I could get more advanced, more exotic, I guess, with how I'm naming these data sets, but I'm just applying them one at a time. You'll note that I got n equal to 6 here. And so when I come to perm.py, I want to comment out the part of the code that involves this data set processing. And now when I save it and I run it, I'll see all this stuff printed to the console, but I'll also see it printed to the output file, which I could upload to Rosalind, or I could just copy it and place it as my answer. It's got a little white space trailing at the end, but that should be okay. And submit, and I see that I've solved the problem correctly again. So Hank, I think you have a good point about the number of recursive calls that you're allowed to accumulate. And that depends on your installation of Python, and it depends on settings that you've set. A lot of times you can manually change your recursion depth, which is the number of calls that you can allow to be sitting on your stack. So yeah, you may have run our code previously and actually gotten a Stack Overflow error from Python when we wrote our recursive approach for Fibonacci, just because of your specific installation. And that will definitely run out of memory on any computer once we establish a value of n that's large enough. Yeah, for sure. All right, I think we can move on. So we need LEXF. It's going to be the next problem that we solve. For our next problem, we're going to look at another enumeration. So we have the question here of having as an input an alphabet, which Rosalind specifies won't be larger than 10 symbols. And then we have a positive integer n, and that positive integer n tells us how long are the strings that we're going to make, how long do they need to be? So what we're going to return is the collection of all the strings of length n that can be formed from this alphabet. But part of the problem is that in this case, we care about the ordering of these things. So we're going to order them what's called lexicographically, meaning using the dictionary order that we would see. Now, I think we can assume safely that the input symbols that we have are also ordered according to this dictionary order. But what we're trying to produce is all the words or strings of the specified length that can be formed from this data set. In computational biology, we refer to a substring of length k or a string of length k, often using the term k-mer, because this is so frequent that we would look at, I don't know, the substrings of a certain length in a data set. So if that length is k, we specify, we use the term k-mer to refer to it. So in this case, I think we've called the input value n, but if we called it k, we would be trying to find all of the k-mers for this particular value that can be formed from this data set. And we are solving this problem downstream of enumerating all the permutations, because what we want to do is apply this exact same approach. I can take each symbol and pull it away, and then in the meantime form all of the substrings of length n-1 from this alphabet. So recursion is lurking around the corner. And then at the end of this process, I'm just going to stick the A back on. So I'm going to range over my alphabet. I'm going to take each symbol. I'm going to form all the substrings of length n-1 from this alphabet. And then I'm going to place each symbol back on the front of everything that I form. So for that reason, we're going to have a function that is similar to what we saw when we formed all permutations. In this case, I'll say we want to take our alphabet as input, and we're going to take a value of k as input. So I've changed n, I guess, here to k, since we've used this framework of calling things k-mers. And we want to return a list of strings. So this is the list of all strings of length k that are ordered how you would see in a dictionary. And to write this function, we're going to think, recursion is near. And if recursion is near, we're going to need a base case. The easiest base case I could have would probably be, well, if k is equal to 1. So we're going to recurse on the length of the strings, meaning if I want strings of length 100, I'm going to generate all the strings of length 99, and then I'm going to place each symbol in the alphabet at the start of all of them. So if k is equal to 1, I'm going to return every single element in the alphabet as a string. And there's a tight one-line way of doing that in Python, which is to just say list alphabet. So I'll just say this returns every symbol in the alphabet as a list of strings. So that's perfect. That's exactly what we want. Then I'm going to specify the result that we want. And just as what we've seen before, I'm going to say, what is it that we want? Well, it's a list of strings, and it's going to start off as empty. And eventually, I'm going to return that result. And in the meantime, I'll say what my inductive step does. It ranges over the alphabet. And for each symbol, it places this symbol at the beginning of all strings of length k-1. So that's where we're going to get to apply our recursion. So I'll range over all the symbols in the alphabet. That's easy to do. And then once I do that, I'm going to enumerate all of the substrings of length k-1. So I'm going to call those substrings. And here is where I get to apply my recursive call. So I'm going to say we're going to still enumerate the k-mers, but I'm going to enumerate the k-mers on the same alphabet of length k-1. So now I've solved the problem in the simpler case. I've gone from 100 to 99, for example. I've got all of those substrings, and now for each of these substrings, plug the current symbol into the start. I don't think that's the right way of, let's say, concatenate the current symbol onto the start, onto it. It's onto its start. Okay, right. So what I'll do is, let's just range over all of these substrings. And I'm going to call this current one suffix. And I want to take what the current thing that I care about is, which is symbol plus the suffix. So this is the current symbol that I've got. This is me plopping it onto the start of the current string. I'm doing this for every single substring that I've obtained. And that's the string that I want to add to the collection of strings that I'm forming. So here's where I will just call result.append of this string. And it seems like magic because this function, you know, fits in 14 lines with all these comments and extra white space in between. And this indicates even though recursion sometimes, as we saw in the case of Fibonacci, sometimes can lead you to an approach that leads to stack overflow and big tree bad and all these issues. In other contexts, it gives you an approach that is extremely short, tight, beautiful, elegant, all of those things. And that if we had to write this function without recursion, it would be a mess. Let's see how it does. So let's go to our terminal and let's run Python 3 of LEXF.py to see how well it's doing on our sample data set. So our sample data set says, in this particular case, here we have AA, AC, AG, AT, and then there's all the things that start with C and all the things that start with G and all the things that start with T. So it seems like we're doing well, and I think we can be confident that we can comment out our data processing part of this and come back to Rosalind and download our data set and ensure that that data set goes into our folder. So we need to go into our File Explorer, and I'll bring this across. I'll delete the previous one. I'm going to call this dataset.txt. And here we've been given this alphabet consisting of 10 characters, and we want to produce only actually the substrings of length 2 of them. So we got lucky that we don't have to make very big substrings here. When I run it, I'll see a lot of stuff gets printed to the console. And there's a lot of substrings here. So in this case, we have 10 options for each symbol. We have substrings of length 2, so we have 10 squared, which is 100. When we look at our output, we'll see all 100 of those things. Good. We actually can see from the line numbers that we have 100 of them, so we feel pretty good here. And we'll take that and copy it back into the platform and submit. And we see that we solved the problem. Good. And Rosalind even suggests a related question that we're going to see soon, which is to create strings of varying lengths up to a given length. And so if we can solve this problem, hopefully we can apply the same sort of ideas to solving this collection of strings of varying lengths. I'm going to look at a different question first before we look at that. Let us know if you have any questions. Hello from Madrid. Welcome. Welcome from Madrid. Welcome from New York. Krishna. We've solved 3 of our questions right now. We're going to solve 3 more. Three more questions to go. My favorite one is the last one, so you'll need to stick around till the end to see that. I'll have some comments about the last one, but in short, I can't believe how many people have solved this question. I'll come back around to this and say it more. It's like one of the meanest questions that I ever could have come up with. And I'm not sure, I think it sort of was like early on in the platform, in the days of the platform, when I was just sort of making fun questions. And I don't know if I realized, eventually this would reach a lot of people. And if I was thinking that this was going to reach a lot of people and I was maybe the older, wiser version of me that I am now, I don't know if I would have put this as one of the introductory questions, because it is an absolute nightmare. And I want to go and give a hug to all 14,400 people who have solved it, because it's just not easy. But we're going to save that one to the end. So stick around for that. That's our final boss today. I think it would be a good idea if we had like a really challenging one as one of our last questions, or our last question every day. We'll see if we can handle that for all of our streams. But I'll make more comments about this when we come back to it at the end, because what's nice is this final question we're going to look at is very related to the rabbit's question that we saw before. It's a very tiny change to it. And as a result, it's just way harder. So we'll save that for now. Yeah, Krishna, I think I accidentally posted the link to episode 1 in our weekly email. So you might have clicked on that, and that's my bad. You can always get notified about upcoming streams if you go to our YouTube channel, and you'll see the schedule of what we have coming up. You can kind of click to get notified, and it'll make sure it sends you a push notification and so forth. So you'll get the link to that. And then we always post on Discord like a few minutes before we start with the updated link. So if I ever have an incorrect link, you can usually find us pretty easily. All right, let's look at one more question. Our next question is going to be sign.py. I'll close out some of this other stuff. We've already solved a question where we looked at enumerating all of the permutations of a collection of integers or collection of objects. And in that particular case, it was easy for us to at least count the number of such things, because we could say, well, if you're rearranging n things, you have n choices for the first one and n minus 1 for the second and n minus 2 for the third and so forth. And the product rule says just multiply all those numbers together and you're going to wind up with n factorial. This question changes that a little bit by saying, well, you also can have a sign. And the reason why is if you're thinking about a biological application here, you may have genes on a chromosome or collections of genes that line up. If you compare us against one of our mouse X chromosome against a human X chromosome, you're going to see a collection of genes that line up, and it's as if big blocks of these genes have been rearranged and moved around. A lot of times what happens is the genes switch and they go to the opposing strand of DNA. So as a result, a better mathematical model for the collection, the ordering of genes or these blocks that you see on a chromosome, a better mathematical model would also take into account signs to indicate that sometimes, as a result of a genome rearrangement event, you wind up with a gene or a block that goes to the opposing strand of DNA. And the direction of that is important, so it should be part of our model. So when we're enumerating all of the ways in which you could order these genes or order these blocks on a chromosome, it would make sense to not just consider the ordering of these integers, but the ordering along with being able to assign a sign to each of the elements. And that's going to change the number of these sign permutations that we have. So before, if we had a positive integer n equal to 2, we had 2 factorial total permutations. We had 1, 2, which is here, We had 2, 1, which is here. Now, though, you'll notice it's as if we have a bunch of copies of 1, 2 and a bunch of copies of 2, 1. And we can formalize how many of these copies there are going to be. Notice that for each of these permutations, you can have a plus sign or minus sign at the front of each element. So it's, if I have a permutation of length 2, I want you to think of this as a binary choice, or like flicking a switch on or off at the start of each of these elements in the permutation. So I have 2 options for the first sign. I have 2 options for the second sign. Whichever way I flip those switches, it's going to give me a different permutation. So I have 2 times 2, which is equal to 4 different choices for how I can flip those switches. If in the case of an arbitrary input integer n, well, I've got 2 to the n choices, because I have 2 choices for the first one, 2 choices for the second, 2 choices for the third, all the way up to the final nth element. All of those choices are independent of each other. So we use this same product rule again to say how many different variants of a given permutation are there. Well, there's 2 to the n. So as a result of this, I have n factorial total permutations in the unsigned world. But in the signed world, each of those is then going to give me 2 to the n different variants based off of all the different signs that we can have. So where does this 8 come from? It comes from the fact that we have n factorial permutations times 2 to the n variants for each one. So our general formula here is 2 to the n times n factorial. That helps us understand this, because when we enumerate it, I know that I definitely want to see the number of such elements be equal to 2 to the n times n factorial. This might at first, if we've solved the permutations problem, where we formed all unsigned permutations of a collection of n things, this might at first seem like a much harder question, right? But we want to apply the same idea that I just presented, which is, why don't we make all of the permutations in the unsigned world? And then for each of them, I'm then going to create a bunch of copies of them where I assign all of the signs. So sometimes you'll see a very elegant algorithm that doesn't necessarily match human intuition. But this is an example of a problem that we can take that idea that I presented just in terms of looking at the sample of saying, let's generate 1, 2 and 2, 1, and then let's generate, I don't know, 2 to the n copies of that, and then figure out how to assign the pluses and minuses accordingly. This is an example of that nice intuitive approach being also a pretty elegant approach that we can apply on the level of code. You'll notice then that, well, the function that I want to write is this function sign permutations that takes an integer n as input and produces a collection of permutations again. So it's a list of permutations, and those permutations at any given point in time, each permutation is just a list of integers. We know that there's going to be 2 to the n times n factorial of these sign permutations. And that's the function that we want to call. Now, when we write that function, the question is, how do I use the fact that I've already written a function called permutations that handles the unsigned case? So I know that that is, as we're following along, I've written that function already, which is this nice recursive function that we produced before that takes a collection of integers, and then it produces a list of all permutations of those integers where we're not changing the signs. So I've got that function already. It comes from perm.py, and I'm simply going to import it when I write this function in sign.py. So at some point in time, in my signed permutations function, and I have a helper function here that I'm going to show you how to write, but at some point in time, I want to produce perms equal all permutations of something like the first n integers. So in this case, the reason why I want to do that is because signed permutations is just going to take an integer n. And what we wrote in the case of perm was actually a little more general. It's going to take a collection of integers. So this could have taken a list of the integers 4, 17, and 19, and then it would have permuted all of those, which is good. This is asking something a little bit more specific, which is just always going to generate all signed permutations of just 1 to n. So I know that this function call is going to be there at some point, and I'm just going to write it down, and I can comment it out if I want, but I'm just going to ensure that I know I need to call this permutations function at some point in time. In the meantime, I'm just going to say, well, let's define the result to be what I care about, which is a list of integers, and that's what I'm going to return. So it's an empty list at the start, and then I'm eventually going to return it. And then in the meantime, I want to say, all right, well, I'm talking about the first n integers here. What do I mean? I mean that the first n integers is really, it's the range of everything between 1 and n plus 1. So I want to start at 1. I don't want to include n plus 1, so I'll go from 1 to n. And then I want the list of these things because, well, when I call permutations, it requires us to input a list as input. So let's have this call here to say perms is equal to the permutations of those first n integers. And now I want to range over all these permutations and assign all possible sign combinations to each one. So there's nothing wrong with just saying for the current permutation in perms. So I'm going to call perm the current permutation. And here's an opportunity for us to apply something that I like to call structured procrastination, which is to say, well, what is it we would like to have? What would we like to have? And in this particular case, I'd like a list of lists, okay, where each individual list tells me the corresponding signs to apply to the current permutation. And these are going to be like +1 or -1. So once I have that list, I can simply range over the current permutation, and then I'm going to multiply it, each element, by whatever is in this collection of other values. So if it's a 1, I'm just going to keep it the same. If it's a -1, I'm going to flip the sign. And that will allow me to imagine that I've got a helper function that I'm going to call sign combos. And it's going to take n as input. And then it's going to produce exactly what this is, a collection of all of the different ways. So it's going to be a list of things, and each individual value is going to be a list itself, which is going to be a collection of ones and negative ones. Okay, so the signs is a list of +1, -1 values of length n. And so then all I have to do is to range over all of the elements in signs and to say, well, what I want to do is to form a signed permutation which starts off as empty, and I will build it up by saying the current signed permutation is going to get signs of I, which is a +1 or a -1, multiplied by perm of I, which is whatever the current value of the permutation that I'm looking at is. So this is nice. So I have a single permutation, and then I'm ranging for each possible collection of signs. I'm going to go through and take that current permutation, multiply it by the signs values, and that's going to give me this sign permutation that I care about. At the end of this process, when I get to here, I now have the sign permutation. I've ranged through and I've set its values. So I want to append it to this result collection that I have. Now, I think I called it results. Let's call it result. I think that makes it consistent with where we've done this in other problems. And what's interesting is that at this point in time, we've not actually applied any recursion. So I don't have a recursive approach here. It seems like recursion should be lurking, but in this case, I've just said, well, assuming I can generate all these sign combinations, for each individual sign combination, I'm just going to multiply plus 1 times the current value if it's a plus 1, or minus 1 times the current value if it's a minus 1, and generate all of my sign permutations here. So in other words, here is where n factorial lives, and here is where the 2 to the n lives. And so when you combine these two nested loops together, that's why you know that you're producing the correct number of sign permutations. So you have a nested loop of length 2 to the n inside one that has length n factorial. Of course, it remains for us to write this sign combos function, so I should do that as well. And here is where the recursion is going to live. So what does sign combos do? It takes as input an integer n, and it returns all of the possible 2 to the n sign combinations as lists of positive 1 values and negative 1 values. So it's again a list of things. Each of those things is a list of integers, but the integers have to be plus 1 or minus 1. So we're going to have a base case that says if n is equal to 1, well, this is an easy list to return. So I want to return a list, and then it's a list of lists. So one of those lists is going to have a 1 in it. The other one is going to have a negative 1 in it. Otherwise, I want to specify, well, I've got a result. It needs to be a list of integers, and it needs to start off as empty. Eventually, that's what I'm going to return. And now the inductive step just says apply. So it's the same sort of idea that we had before. Concatenate plus 1 and minus 1 to all possible sign combos of length n minus 1. So I will say for whatever the remainder is in, and I'm going to call this sign combos, call the function sign combos of n minus 1. So this will give me all the list of all possible sign combinations of 1s and minus 1s of length n minus 1. And once I've got that remainder, I'm just going to say, okay, I want to add a plus 1 to everything here, and a minus 1 to it to give me 2 combinations. So I will say result.append, okay, and I'm going to say the list 1 plus the current list that I'm looking at, and I'm also going to append to the result list the concatenation of minus 1 and the remainder. And again, magically, we have a very short, very tight recursive function that does something pretty complicated, right? Which is to form all possible sign combinations that we could assign. So we have 2 to the n different lists that are getting produced from this. And there's an iterative or non-recursive way of doing it. But once we see this idea that I can just take a 1 or a minus 1 off the front and reduce the problem to say I'm just looking at the list of all things of length n minus 1, and I'm adding a 1 and a minus 1 to that entire list, we get to apply the same idea that we've seen before. Now I can run the test data set. Hopefully everything is in order. I'm going to run sign.py. Here's our sample that we saw before. We're getting the correct number. So this is just printing in main. What it's printing is the length of sign permutations, which we knew to be 8 when n is equal to 2. And we can print these in any order, but here are the permutations corresponding to 1, 2. Here are the sign permutations corresponding to 2, 1. And I think we should feel comfortable that we can comment out our doc string here and run this on a larger example. So let's generate a data set for ourselves and put that into our file explorer and name it dataset.txt. And it gave us a value of n equal to 3, so we're going to get 2 cubed, which is 8, times 3 factorial, which is 6. So when we produce this, what we're going to see is we should have 48 total things, which is what we see there. And they got written to output. And so output has the number that we have, which is 48, followed by the sign permutations themselves. You See all the different ones. Pretty neat. And we can put it back into our submission, and we see that we solved the problem. Hooray. Two more questions to go today, and then we'll wrap up. One more until we get to our final boss. So we're going to look at Lex. I think it's LEXV, not LEXF. LEXV is going to be our next question that we look at. We're going to have two tough ones to finish up here today. For our next question, we're going to look at LEXV, which asks us to take a collection of symbols, as well as an integer n, and to return all the strings of length 1 up to n that we could form from our alphabet. So if we had, for example, the sample data set DNA, we're going to get everything of length 3, which is a problem that we've seen before. But then we're also going to need to generate all the strings of length 2, and of course all the strings of length 1 as well. There's a natural question here, which is, for an alphabet of length k and a string maximum length equal to n, how many strings are there? That's an interesting mathematical question. It's probably a little beyond anything that we've currently asked as a, what's the formula for this thing? So come to our Discord, let us know if you have a solution there. I'm going to save that though. And we want to write the function to actually produce these strings. So we've written a similar function, which lexicographically ordered or ordered as they would appear in the dictionary, a collection of all substrings or all strings of a fixed length. But here we need to do this for all strings of varying lengths. And the fact that we need to order them lexicographically is what makes this problem challenging, because I could always, if I weren't interested in doing that, I could always simply call the function that I wrote here for every input value up to n, right? And I could get those strings. But the problem is that I want to make sure that I produce those strings in this dictionary order. So I need to return them in this way. There's two ways of doing this. One way of doing it is just to do that and then to call a built-in sort function. So that is a perfectly reasonable way of solving this question. I'm going to show a way of solving the question with a more optimized algorithm that I think still allows us to apply recursion, the same sort of technique that we saw when we generated all strings of fixed length, but nevertheless at the same time is going to do so in, I think, an elegant way without calling this subroutine. For the very fancy, I'll say one more thing, which is that this collection of strings is technically going to be a depth-first search of the trie or keyword tree or prefix tree of all of the substrings that we care about. Okay, and those substrings that we care about are all strings that can be formed from this alphabet, having length equal to 1 up to our integer n. That's a good pointer for some problems that we're going to look at farther down the line. But for now, I want to not think about the problem in that way, and I want to pick a middle ground between a very fancy way of thinking about it, as this depth first search, and the kludgy but reasonable way of solving this question, which is to solve it for an input value equal to 1, 2, and 3, or everything up to n, and then just to call a sort function to combine all these things. Can we do it ourselves? So to do this ourselves, I'm going to want to write a function called enumerate strings that takes an alphabet as a list of strings, and it takes the length that I care about, and I want to return a list of strings where it's all possible substrings of length up to length n formed from that alphabet. Now, I'm going to pass a lot of my work here to a subroutine. So I'm still going to use this notion of setting result is a list of strings. That's what I want. It'll be empty. Eventually, that's what I'm going to return. And I'm still going to use the idea of ranging over all the symbols in the alphabet and taking each one and then trying to add them in. Okay, so I'm going to say, what are the, let's say, 4 symbol in the alphabet? I'm going to have a lengthy variable here. I'm going to call it strings starting with symbol. Okay, so what are all the strings that start with that symbol? And that's going to allow me to say, well, I'm lexicographically ordering everything, but I'm going to, if I have A, C, G, and T, for example, I'm going to start with the A's, and then I'm going to start with everything that is a C, and then everything that's a G, and everything that's a T. So I'm going to assume here, I think that the alphabet itself is sorted. And when I do this, I'm going to say, all right, whatever this collection of strings is, I'm going to call a function to get it called extend strings. And this extend string function is going to take the alphabet, of course, and it's going to take an input integer n, and then it's going to take the symbol that I care about. I'm going to talk about it here momentarily, but in the meantime, I'm just going to say, let's range through that collection of strings, and then I'm going to append the current string s to that result list that I care about. Right? So I've really just passed the work to a function that's called extend strings that takes the alphabet, it takes the length n that I care about, and it takes the symbol, and it's going to extend, using the alphabet, it's going to extend this symbol into all strings having length up to and possibly including n. And once that function has done its work, it's going to give me this list. I'm going to range through all of those strings that I get and append them to my result. So I've done this for every symbol in the alphabet. And what is fascinating about this function that I'm going to write as my helper is that it's still going to be recursion. So we get to see recursion yet again in the context of building out or enumerating strings or whatever it is that we're working with. But this function is going to be based off of a base case that is, most of the time, when you write a base case, the base case is always like if n equals 0, or it's like if n equals 0 or n equal to 1. And then we do foo, okay? Or return blah. Now, this is going to be a very weird recursive function because most of the time our base case is something tiny. In this case, we're going to stop the recursion when we continue extending the strings and when we hit a value of n. So weirdly enough, I'm going to start this, the recursion is going to operate on n is going to be fixed. Alphabet is always going to be fixed. So I'm going of strings up to length n, and it's current That's going to be where I apply the recursion. So I'm going to start with a single symbol as whatever current is. And then what I'm going to do is continue building it up into larger or larger strings, which means that the base case that I'm going to hit, amazingly, is going to be if length of the current string that I'm working with is equal to n. And in that particular case, I'm just going to, well, I'm returning a list of strings. And if I have a string of length n, then I just want to return it. So I'm going to have a list of just the current string. And you know what? Let me specify, I can call it current string. So just a little bit more descriptive. And then we apply induction. And so the idea of induction is to extending the current string by all symbols in alphabet. Because at this point in time, I know that the length of the current string, at least for the data sets that we're going to get, is less than n. And you could, of course, add a check here to see what happens if the length of the current string is greater than n. Maybe you produce an error. But for the data sets I'm going to work with, I know that the length is always going to be less than n here because I've made the check of what happens if I ever hit n. So I'm going to get bigger and bigger. If I hit n, I'm going to hit a base case. So for this function, I'm going to say, well, take every symbol in alphabet. If I'm extending the current string by all symbols in the alphabet, I don't even need that comment. I'm just going to say for symbol in the alphabet. And as I go through the alphabet, I'm going to say, well, we want to extend these things. So what are the strings starting with this particular symbol? I want to extend the strings in the alphabet up to length n of this symbol. Okay. And let's see. Actually, I'm in the wrong place. Symbol in alphabet. No, this is the wrong place. Sorry. Okay. What we actually want to do is range over the alphabet and do something simpler, which is to say, form all of the extended strings that I have. So let's say I'm going to call this extended strings, and I'm going to extend the strings based off of taking the alphabet, which I said is never going to change. N is not going to change because we're going up to and including n, so that's our threshold to say where we're going to stop. And then here's where I'm going to take the current string, and I'm just going to append symbol to the end of it. So we're taking the current string and extending it by all possible symbols. And when I do that, once I've got that collection of extended strings, I just want to range over all these things. So I'm going to say range over all of these extended strings with some string s. And once I do that, then I'm just going to append s as a result. And I want to make sure that I don't forget to return the result that we have. So I've used result here. I probably should specify here. That's going to be the collection of strings that we're eventually going to return, and it needs to start off as an empty list. So we recursively apply the function. What does the function do? It generates all the extensions of this current string up to length n. And so the recursion now is going upward, which is to say I've got the current string, extend all of the strings for each symbol in the alphabet by just adding that symbol on to the end of the current string. Let's see if this even works. So we're going to run Python 3 of LEXV, and we see that we get this collection of strings. Now I didn't sort them because actually the alphabet is specifying this is the order that I care about. So it's a fancy question from the perspective of we're going to specify actually that the order that we care about is D, then N, then A. And that kind of prevents you from using a built-in sort because the built-in sort is going to treat A as the first symbol, and this ensures that you do it manually, which is kind of clever. This appears to be working reasonably well then. I'm going to uncomment out my dataset processing. We can now solve this question, download the dataset, and I'm going to move it over into my file explorer as dataset.txt. And now when I look at my data set, this is saying that the order that I care about is R, then S, then G, then P, and so on. And when I run this again, and hit up, I get here is my list of strings. Hopefully I'm seeing some, I think I ran the wrong LEXV.py. Okay. Look at the output that we have. I'm a little worried here because I don't have any strings of length 1. So I know that this is going to be wrong. It seems like maybe I've actually just resolved LEXF, which is weird, but you know, let's do the right thing and say I know this is going to be wrong. Instead of letting it time out, we can just give it the wrong answer. Okay. So we need to fix it. And come back to LEXV. We can comment this out. All right, so we see the same thing with DNA. I should have noticed that before. We're not actually generating things of variable lengths. We do appear to be generating all of the strings that we had before, but for whatever reason, we're just not quite getting all of our strings that we care about. So I think, we know that this is not right. I think that it's probably pretty clear that it's in the extend strings subroutine that we need to fix this. So base case looks good. There we go. This would be very easy to miss, but we set this to be equal to an empty string. And one of the things that we forgot to do, which is when we extend the strings, we're just going to keep extending a symbol on top of the current string, and then we're going to append that to S. But if you're thinking about this, well, at what point in time are we ever extending or are we ever appending like a single symbol string to our result list? That never actually happens. So I want you to think like when we call enumerate strings, we have this issue where I start with a single symbol, and then we want to extend and create all strings that start with that symbol up to the length that we care about in. But at no point in time are we allowing ourselves to just append that symbol. And that's why we're creating a problem. We keep extending the strings and then we append that, but where did I add just the single symbol? And the issue that we can fix here is that when we create the result list that we care about, I need to make sure that I remember to put the current string in there, because we're extending all of the extensions of it, but I neglected to put the original string in the list. So we're going to start the list. I was so used to just setting empty lists. Our result list starts with the current string. This will ensure that we'll have symbols with, strings with a single symbol. And then when the recursion happens again and we extend them to have length 2, well, those length 2 strings need to make sure that they get added here too, and that's going to handle it. So let's see if this handles it. Hopefully what we should see is, we're starting to see single element strings, we're starting to see double element strings and so forth. And now I can maybe go back and try this again. We had probably a minute timeout on the platform, but we can run this again, and hopefully I'll see this for this data set that we had before. Hopefully we'll see this vary, and we see that indeed. Okay, so we see single elements and 2 elements. Let's go back to our platform and try this again. I'm going to delete my data set and grab another data set from the platform. Try again. Go to my file explorer and put that in there as dataset.txt. And now when I hit up and run this again, I'll look in my output. And my output, this case, gave me an n equal to 4. And so we see strings of varying length in there, which is what we needed. It's weird that we solved the LEXF problem in a very roundabout way. And I've copied that in and submitted. And we see that we solved the problem. Good. So that shows how carefully we need to establish base cases, and when we apply induction, how one tiny little thing can give us a very different result. I can delete my big tree bad now. So we've got one more problem. Our final problem today is called FIBD. This is our final boss. And if you follow the rest of the stream, you might say, well, some of these problems are challenging too, right? Well, just wait. And it's not actually the code itself for this problem that's challenging. It's going to be figuring out why the code works. All right. So our final question is going to be FIBD on mortal Fibonacci rabbits. We have a simple counting problem here, which is that we have already taken a look at a Fibonacci sequence in the case of adapting a Fibonacci sequence to this idea that you start with one pair of rabbits, and in every generation, the reproduction age rabbits, which have lived for a month already, produce K rabbit pairs. The mortal Fibonacci rabbits problem modifies this to say they're only going to have one pair of rabbits as offspring, but all the rabbits are only going to live for M months. So as we saw in the case of the first Fibonacci problem that we looked at, the first thing that we should do is to make sure that we understand how the counting is going to work. So if the rabbits live for 3 months and we start with, and we're looking at what happens after month 6, we should make sure that we get the value of 4 here. And we've got a figure here to explain and understand all of this, but I want us to reason through this and make a table before we do anything. So I want you to imagine that we start with, so this is going to be, let's look at M equal to 3. And for M equal to 3, we're going to have a month, and we're going to have a number of pairs. And our first month is going to be an easy month that's 0. We're not going to have any rabbits. In month 1, we're going to have one pair of rabbits. So this is the first collection of rabbits that are born. So this is rabbits live for 3 months. And then we're going to look at month 2. And the number of pairs of rabbits there is going to be 1. Why? Because, well, the rabbits that started off that were born in month 1 are now adults. Which means that when we go to month 3, they are going to produce one pair of offspring. And they have not died yet, but they are going to die when we go to month 4, but not before producing another collection of offspring. So they're going to produce a collection of offspring, but they're also going to die. So we're going to say, well, you had 2 pairs of rabbits from the previous generation. You have one collection of offspring, so you go to 3, and then one of them is going to die, so you go to 2. And then we're going to look at month 5, And this is where things are going to start to get tricky, because I need to remember, well, how many offspring are alive or old enough to be of reproduction age? And this is where things are going to start to become quite complex. So I'm not sure that I would be comfortable being confident in producing these values at this point in time. It's not clear at all where our recurrence relation from before is going to arise. So in order to find a pattern, maybe I just make a bigger table. Okay, because it's hard to keep track of how old everything is. So if we're going to keep track of how old the rabbits are, let's try something a little different. So I'm going to have a month, and here's where I'm going to say number of babies, and then we're going to have number of 1 month, and then we're going to have number of 2 month, and then we're going to have the total. And the total is what I care about. That's what the problem is trying to ask us to do. So I'm going to say at month 0, we're going to have no babies, and we're going to have no 1 months and no 2 months, and the 3 months are all going to die. So the total is just the sum of all this stuff. Then we're going to go to month 1, and we have our first collection of rabbits born. And we're going to have 1 month, 2 month, and the total is going to be 1. And we're going to keep thinking through this. So in month 2, we have no babies, but the original pair has grown up to be 1 month old. And then we have no 2 month olds, and then we're going to have a 1 in the total. Then we go to month 3, and we say, well, we now have an adult pair, so we're going to have newborns, and then we don't have any babies that are growing up into 1 month olds. So everybody here is going to go 1 over and down to the right. So we can see that pattern happening. So the 1 month pair becomes a 2 month pair, and then the total now is 2. So everybody from the previous generation goes over 1. And if you have a 2 month pair, then it hits the mortality rate, and it doesn't contribute to the total in the next generation. So now I've got an easier way of counting this. So in month 4, the 2 month pair produces another collection of offspring. These babies become 1 month old. The 2 months age out of the model, and we still have a total of 2. Then when we hit month 5, now I have this question mark value that I was finding it hard to reason through, and I'm going to be able to compute it because the number of babies is equal to the number of 1 month olds. So we put a 1 there. And then these babies become 1 month old, and these 1 month old become 2 month old. And now we have a value of 3. So now I can confidently say that that should be a 3. And I'm going to be able to compute 6 also, which is what the sample data set was trying to tell me. In fact, I can compute these all day. I can see what the pattern is, right? I add up the 2 adult columns, and that's going to tell me what the collection of offspring is going to be. And then everybody short of 2 month moves over, and then we have the 2, if there anything here in the 2 month category from the previous generation, then that's going to hit our mortality rate. So we're going to say at month 6, how many pairs of babies do I have? Well, we have 2 pairs of adults, so 1 here and 1 here, so that's going to be a 2. Then we say, well, the babies become 1 month old. These become 1 month old. And now I can say that this value is equal to 4. And so I can set that now equal to 4, which is what the test tells us we should be getting. And here is the pictorial representation of it. But the pictorial representation of it, I don't think makes it as clear in terms of how to compute this. So we come back to the same learning lesson that we saw previously when it comes to counting something. The absolute first thing that I have to do is understand how it is that I might count this by hand. And if I just keep track of a single tally and I don't know how old everything is, that's going to be really hard. And as a result, this became much easier when I went to a larger table. Now, what I would love to have is a recurrence relation here, because there are 2 ways of solving the problem. One way of solving this problem is to make all of these tables. So in general, here, the number of months that we have m that each pair of rabbits live for is equal to 3. And so we have 3 columns of our table. So we could keep track of this in general with m total columns, right? But then this is going to become a lot of equations that are going on behind the scenes. What I care about really is not keeping track of all that, but being able to determine what the total is. So if this total is t of n, that's what I actually care about. And the second way of solving the problem would be to say, is it possible to just form a recurrence relation for t of n? Is that something that we could, in theory, do? And it is completely unclear how we would do this. And if your solution to the problem is just to keep track of all these tables, I think that's a great, very straightforward and intuitive way of solving this problem. You might actually solve the problem initially that way. And I bet a lot of the people, at the time that I'm showing this, we've had 14,000 people solve this problem. I bet a lot of those 14,000 people solved the problem in this way. They very carefully wrote out the table so that they could understand it. And then they produced basically a big 2-dimensional array, and then they entered all these values, and then they summed them as we go. Now, I wrote this question as a mathematics PhD student, which means I looked at the problem and I thought, oh, this is going to be straightforward. Yeah, it's just Fibonacci rabbits with a mortality condition. So there's a recurrence relation there, and it's a straightforward problem to solve. There's not a whole lot. It's a great introductory question, but it's just introducing people to counting, and that's all it is. And now I've come back to this question after over 10 years, and I've thought, how is it that you actually solve this by getting just the recurrence relation for t of n? That's what I really care about. And I had a real Gandalf moment staring at the door and not knowing how to open it and thinking, I really do not know this place. And I had to sit here and think and try to work this out and figure out a way of taking every ounce of mathematical energy I have left in my old body and trying to figure out a way of solving this question. Because it turns out that this is not easy. And I've even seen solutions to this online, and I might just be looking in the wrong places. And I don't think that there's a good explanation of this question on the internet. So let me try to give you something that is at least a start of explaining this. This is actually a fantastic teachable moment in the sense that sometimes an answer can kind of come out of nowhere without an intuitive explanation. And so the intuitive explanation for this problem is this. But it turns out you actually can get a recurrence relation for t of n, and understanding what that recurrence relation even means is completely unclear. The only way I can make it clear to you is to show you a bunch of algebra. So the way I'm going to do this is to say, let's write down what we know. Now, I'm going to define b of n is equal to the number of births in month n. And if I write that down, well, I can use that. And what I would care about here is t of n, which is the total. So t of n is total number of pairs alive after month n. All right, so we've got both of those things. And then there is a relationship between them, which is we've already kind of seen from making this table. And it's close to a recurrence relation, but it's not really, because what it says is the total number of rabbit pairs alive in month n, or at the end of month n, is equal to, it's kind of the number that you had in the previous generation. Because a lot of them, especially if m is big, which is the number of months they live for, a lot of them are just going to survive. So in this particular case, we know that the total here is in some sense related to these collection of rabbits. But then we need to make sure that we subtract this away. And we also need to add our birth condition. So it's the number that were alive in the previous generation plus the new births minus the new deaths. And then we're going to say, well, can I represent that in a certain way? And I now have a formula, or an expression, I should say, for the number of new births, and in particular in month M, and minus the new deaths in month N. And so I'll say T of N is equal to T of N minus 1 plus the number of new births. Well, that's just B of N. Great. And I also have the number of new deaths. Now I could specify that as its own formula D of N, right? But it turns out that then D of N is related to B of N in a specific way. The number of rabbit pairs that are going to die in month N, if I think about, well, these collection of organisms are going to die in this generation. Well, where did they come from? They were here, and then they were here, and then they were here. So in general, what I'm saying here is you're going to be looking M generations previously for the number of rabbit pairs that were born, M, which in this case is 3, M generations previously. So they're born here, 1 month old, 2 month old, and then M months old, and they no longer contribute to T of N. So when I subtract out to say what are the new deaths, they're the rabbits that were born in generation B of N minus M, or in generation N minus M. So now I kind of have a recurrence relation, except not really, because the recurrence relation that I have also has this B of N stuff and B of N minus 1 stuff. So I'm down to like needing 2 tables. And I could solve the problem in that way, I guess, if I were to know how many adult rabbits there are. I could figure out what the birth rate is in month M, but I don't really know that yet. But what I'm at least going to do is to say, this is Formula 1. Not Formula 1, the racing. Say Formula number 1. Okay, so I'm going to remember that. It at least looks useful, which is that the number of rabbits in the current generation is the number of the previous plus the number born minus the number that died, which is this relationship of the ones that were born in month N minus M. Another way of writing this is to take all the T terms and put them on one side, and all the B terms and put them on the other side. So I'm going to say T of N minus T of N minus 1 is equal to B of N minus B of N minus M. That's just a little bit of algebra. And it's convenient sometimes in algebra to have one function on one side of the equation and the other function on the other side of the equation. Turns out that's going to be super useful here momentarily. Okay. We also know about the birth rate. So we also know that the birth rate in generation N is the number of adults in generation N minus 1. And so we can represent this by saying, all right, well, that means that B of N is equal to whatever the total number of rabbits was in generation N minus 1 minus, say how many were born here? Well, it's the total, which was all these adults, minus the number born. So it's T of N minus 1 minus B of N minus 1. And you're starting to see, I don't know, you stare at this long enough and you think, can I somehow combine this fact, which is, this is formula numero dos, and how do I combine this with this? Because they both are equations involving T and B. Maybe somehow they're going to come together magically. So for them to come together magically, what that means is maybe I could substitute this in as my B of N here. Okay, so I'm going to take this expression and place it here for my B of N. And maybe that goes nowhere, but I'm going to say combining 1 and 2. That's going to give me, all right, let's look at formula number 1. It's T of N is equal to T of N minus 1 plus, now this expression for B of N. And then I've got still minus this thing, which is B of N minus M. Or in other words, I've got 2 factors of T of N minus 1. And then I've also got my minus b of n minus 1 minus b of n minus m. And I hope that if nothing else, this is a demonstration of how mathematics can drive one to madness. Because after all, everything that I've said makes perfect intuitive sense. But me as a human, I as a human look at this, and I think it's not clear whether or not any of this collection of true statements is actually leading anywhere that's going to be useful for me to solving this completely make-believe question about rabbits that was only intended as a way of practicing dynamic programming. So then the question is, do we see anything here that might lead us somewhere? And we've got 2 times t of n minus 1 minus b of n minus 1 minus b of n minus m. And in this particular case, we can say, well, this term seems a little bit annoying. I'm going to do something, which is to say I'm going to notice that this also I could just apply formula 2 again. So let's apply formula 2 again. And I'll say t of n is equal to 2 times t of n minus 1. And we're going to say minus b of n minus 1. And then minus, when I take formula number 2, I want to say, yes, I'm working with b of n minus m. So whatever this input is this input. So I'll take the right side here, and I'll just substitute in n minus m for n. And I wind up with t of n minus m minus 1 minus b of n minus m minus 1. And you say, I'm certainly mad now, right? Because I could arrange this and at least get the t terms over here and say t of n is equal to 2 times t of n minus 1 minus t of n minus m minus 1. And get this out of here and then move this thing over here. So when I move this expression into here, I'm going to say this is minus, in brackets, b of n minus 1 minus b of n minus m minus 1, which is that term that we had before. So again, still just a little bit more algebra. And then I look at this expression. And that expression should feel a little bit familiar, because this expression is the number of births in generation n minus 1 minus the number of births in generation n minus m minus 1, which is really like m generations previous to this generation. And we think we can get lost in the formulas, but that has a very clear meaning to me. And it's actually something that I've seen before, which if this is the birth rate, this essentially is the birth rate in generation n minus 1. This is the death rate in generation n minus 1, because it's the collection of rabbits that were born m generations previously. And you say, well, the birth rate minus the death rate, I've actually seen that. This is the birth rate here in generation n. This is the death rate in generation n minus m. The only difference between these is I have an extra minus 1. So I get to use this formula here and substitute in here and say t of n is equal to 2 times t of n minus 1 minus t of n minus m minus 1 minus everything that's in here. I will apply this formula. The only thing that I have to do is say, it's m minus 1. And this is a minus 1, so I need to subtract a 1 there and subtract a 1 there, and I get that this, in this expression, has to be t of n minus 1 minus t of n minus 2. That's just the difference in the populations between these two consecutive generations. And this is applying the alternative formula 1. Now what have we done? We now actually magically have everything in terms of the total. We have a formula for t in terms of the total number of rabbits at different times. And you actually get a little bit of simplification, because I get this 2 times t to the n minus 1, and I subtract out a t of n minus 1 term. And so we wind up with t of n is equal to t of n minus 1 minus t of n minus m minus 1. And when you subtract this term here, this flips to a positive, and I'm going to put it here and say t of n minus 2. So this is the exclamation mark, because here we now have a recurrence relation for the total number of rabbits alive after month m, or generation n, in terms of previous values. It says that the number of rabbits that are alive at time point n is equal to the number that were alive in the previous generation, plus the number that were alive in 2 generations previously, minus the number that were alive in after month n minus m minus 1. And that's an amazing formula. And what you think is, well, we had a similar recurrence relation if you followed our discussion of the Fibonacci sequence. That made a whole lot of sense, right? Because we said the number of rabbits alive after I generations is the number that were alive in the preceding generation, plus the number of adult rabbits in the current population, which was represented by this population, times the number of pairs that they make. And everything is right with the world, because you can see that that formula makes perfect sense. If you try to find, where you will be driven to madness, is if you try to find a nice, short, intuitive explanation of why this formula should be true in terms of those populations. It just falls out at the end of the day. There isn't a magical explanation of, oh, well, these collection of rabbits survive and these reach adulthood and these die. It just doesn't exist. And yet we wind up with this beautiful recurrence relations, nevertheless, in terms of the total number of rabbits. And that helps us create an algorithm, because it means I don't need to store all of these different tables telling me how many of each age of rabbit do I have. I just need to store t of n. And that means that I just need to write a function, mortal rabbit pairs, that's going to say, well, I've got a Fibonacci array. It starts with a bunch of zeros in it. How long are they? N plus 1, exactly like what we saw when we solved fib. Fib of 0 is going to be 0. Fib of 1 is going to be equal to 1. So this is our first pair born. And then I'm going to range over all the possible generations. And I want to be careful, because the last thing I want to do is to set fib of I equal to my recurrence relation and say, here's where we use, copy down my amazing recurrence relation and say, the last thing I want to do is say fib of I minus 1 plus fib of I minus 2 minus fib of I minus m minus 1. And the reason why that's something that we definitely do not want to do is because if I is equal to 2, when I access this term, I might be accessing something negative, which means that in a real normal programming language, not a functional programming language, but a programming language that isn't badly broken, you get an error with something like that. Now in Python, it's going to give you some negative indexing nonsense, and you're actually going to get a value, and then it's not going to make any sense, and you're going to quit programming because you are not going to have an answer that makes any sense to you. It's going to be impossible to debug it, and then you're going to wind up just vibe coding everything, and you don't actually learn to think about how a computer might solve problems in the first place, and then the snake swallows itself. But in this particular case, I'm going to keep in mind that if I is equal to 2 and m is equal to 12, this is really bad and not something that I should write. And so what we will do is, we need to think through what we're actually modeling. And we need to say that rabbits only die if we're in generation I greater than or equal to m. That's the only circumstance where they have lived long enough to be removed. And so for that reason, we're not going to have that term. We're going to start off with that, and then I'm going to say, if it's the case that I is bigger than or equal to m, or bigger than or equal to m plus 1, excuse me, so that we make sure we don't have an indexing error here. Once they've survived long enough, now we have our subtraction term. Okay, so this is just normal Fibonacci up to the point at which you have mortality. This is all this equation is saying. But then once you start having mortality, I'm going to say, well, fib of I needs to get minus equaled whatever fib of I minus m minus 1 is. And now we have the third term that contributes. And what's amazing about this is the whole point I'm getting at with the beauty of dynamic programming and applying a recurrence relation bottom up, which is that I'm going to get my entire table with just this amount of code. Now, what is the hard part? It's getting the 8 exclamation mark recurrence relation that falls out of this, that doesn't have a really clear intuitive explanation, and that comes from algebraic manipulations after we state what it is that we're trying to find and what it is that we care about and how they relate to each other. Of course, you might say I could just make my tables, but the whole point of effective algorithmic design is to make algorithms that are faster, that don't need all of this memory, and that can go straight to what it is that we care about, which is the total. So our function is done, right? We just need to run it on our tests, and main has n equal to 6 and m equal to 3, so I can save my code, and I'm going to know exactly what this should look like. So I'm going to Python 3 run fibd.py, and I should see, well, I have 0 pairs, then 1, then 1, then 2, 3, 4, 6. And I should see that same sequence when I look at my example on Rosalind. It should tell me, oh, well, there starts with 0 pairs, then there's 1, 1, 2, 3, 4, 6. And do we see 0, 1, 1, 2, 3, 4, 6? We do not. So our wonderful algorithm appears to have a flaw. And the question becomes, what happened here? How do we address this flaw? Our pattern should be 0, 1, 1, 2, 2, 3, 4. And I'll write that down. There's nothing wrong with saying for this specific example, our pattern should be 0, 1, 1, I think we said 2, 2, 3, 4. But instead, our pattern, it is 0, 1, 1, 2, 3, 4, 6. And so it seems like we had this beautiful approach. What do we do? Was the math wrong? How could the math be wrong? It all seemed so reasonable. It was all just algebraic manipulations. So if we trust that what we said was reasonable, and we already know that when we write our function, we have to handle things a little bit differently in our initial generations. Maybe that's the concern. And I want you to notice that m is equal to 3, and what we should do as effective problem solvers is to say, we started building the matrix correctly, and then it broke at this particular position. And then we say, well, what is that position? Well, it's index 0, 1, 2, 3, 4. And we could write this down and we could look at different values of m, but I think it's telling that the value of m that this fails on is m plus 1, because that's m plus 1 is being implicated here and m plus 1 is being implicated here. So if that's the case, then the question becomes, how is it that we handle maybe just this value I equal to m plus 1, or we could at least address just that concern, and it might still be wrong. But what we should do is we should look back at our table. And here again is the benefit of solving problems as a human, by literally writing down what it is that you're trying to count. If we go back to our original table, and we say, the month that we're troubled with is this month. We're producing a value of 3 here, when we should be producing a value of 2. And you'll note that the mortal rabbit pairs in this particular case, we have this recurrence relation gets set, and we also have I equal to m plus 1 where we do our subtraction. And we reason through and think, well, at this point in time, in this row, we can ask ourselves, what died in this month? In this particular month, what died? In this particular month, the original starting pair that we had is what winds up leaving our population. And so we need to make sure that we're subtracting that out. And so what makes this challenging is the recurrence relation is true, but things are becoming a little bit weird because the recurrence relation is based off of like a long-term behavior. And what it's not taking into account is that this collection of babies were not produced from the normal way that we would produce them, which is to say we had adults in the previous generation, and that's where our babies came from. No, they're produced, and it's the only generation where this is the case, where they're just magically, spontaneously generated. So for that reason, that's why this is producing a little bit of a weirdness when I get to generation 4. And what I'm subtracting out is, in this case, m is 3. So n minus m minus 1 is 4. So when I'm subtracting out this value, I'm getting a 0 there. And I should be subtracting this 1 because that's actually what died. And the reason why there's this disagreement is because this is the only collection of babies that you have, the only rabbits that you'll see in this particular very made-up universe that spontaneously generate. So I need to have that particular case handled, right? So our original pair were spontaneously generated, which messes up the recurrence. And I need to say if I is equal to m plus 1, well, I normally would be just subtracting 0 from it, but instead I want to say fib of I minus equal 1. And I'm going to change this to a greater than m plus 1, and it needs to be an else if. So I'll have these two possible cases. If I is equal to m plus 1, we're just going to subtract 1. Otherwise, if you're greater than m plus 1, then you're going to do your normal subtraction. And now when I save it and I run it, do I see what I want? Yes, 0, 1, 1, 2, 2, 3, 4. And that's exactly what we found before as our total. And the magic recurrence relation appears to be working, which means I can come to the platform, download a data set from Rosalind, put that data set into my File Explorer, rename it dataset.txt, and now I've got some pretty big values. So this is 96 generations, and the rabbits are going to live for 19 generations. So hopefully this is going to work. If we get it right, I think we can be pretty confident that we solved the problem in general. But I need to make sure that in main, I comment out my data processing. And save this, run it. Here's my number of rabbits. That sure is a lot of rabbits, even though they're mortal. Grab my output value, copy it in, close my eyes, click submit. And the math is working. So I've rediscovered the magic of my mathematical youth, and everything appears to be right with the universe. I would say I'm not mad, but that one is probably debatable. That's a good stopping point for today, though. We've learned a lot about counting things. We've seen so much here. We've seen when recursion works. We've seen when it doesn't work, where dynamic programming, taking a matrix and building it up from smaller values to larger values, is a preferable approach. We've seen contexts where it's very useful. So for example, if we were establishing all gene orders or all strings of a certain length, you could peel away one of the things that you care about, form all of the things of length n minus 1 that you care about recursively, and then just add it back. We've seen a couple of different, more advanced variants of this, where we form sign permutations. And then we varied the length of the strings that we're trying to form. And we appreciate this difference between counting something, which is how many of something there is, as well as enumerating it, which is generating the list of all of the things that you might be wanting to study. All of these ideas are going to be critically important as we go through the platform. And we're going to come back to counting soon, but we're going to use all of these sort of underlying foundational concepts that we've seen today in order to come back to more advanced questions that involve them, as well as questions that I think are fundamental in modern biological data analysis. So up next, we're going to see all that stuff. We're going to work with strings more. We're going to look a little bit into genetics and the probability associated with that. We're going to take a look into proteins and all the questions that we could ask about proteins at least as strings of amino acids and studying them in that context. And we'll continue streaming. So our streaming schedule is right now Thursdays, 11 a.m. Eastern. We have posted the tentative schedule to our future YouTube streams. So go to our channel, go to the live part of our channel, and you can click to get notified so that you make sure that you're staying up to date with those. Those will have the general sort of problems that we're going to have, and then we'll list which problems that we're going to study as we go through it. You'll also see in our starter code or our completed code folder, you're going to see the problems that we solve. Each week, we're going to continue populating those as we go. But that's it for today. Thank you for joining us. I can't wait to solve some more problems later. We got through some hard math stuff, and now we can use it, now that our brains have gotten a lot bigger, we can use it to solve some more practical questions and some more advanced questions. But you'll have to join me at a later time for all of that. And I will see you then. But until then, all the best. Happy coding.